In today's tutorial, we are going to design and simulate a microstrip transmission line using ADS software. We will use Linecalc to find our physical dimensions for a 2.4 GHz design and then verify everything with an EM simulation. So let's jump in. First, we need a clean workplace. Go to File. Here you can see Workplace, or you can see the new Workplace icon in the toolbar. I will name it as Lab 1. Now that our workplace is ready, we need to create a schematic. Go to Window option. Here you can see the new schematic, or you can find the schematic icon in the toolbar. I will name it as Cell 1. Now for the core tool, Linecalc, go to Tool option. Here you can see the Linecalc. Click Start Linecalc. Here I will set some values. You can set them as you want. Here is our dielectric constant. I will set it to 4.6. Don't change MUR. I will not change MUR. If you want, you can change it. H is our substrate thickness. I will set it to 1.6 and the unit will be millimeter. I will not change HU. T is our thickness. I will set it to 0.7 and I will not change the unit here. I will set the conductivity to 5.8 10 to the power 7 and set 10D to 0.001. Basically, this defines the dielectric loss. It will be better if we keep it lower. We will set our frequency 2.4 GHz. Then our characteristic impedance 50 ohm. You can change the phase shift if you want, but I will not change it. Then before clicking synthesize, we need to set the physical unit in millimeter. Then click synthesize. By clicking synthesize, Linecalc give us the required width for our trace. Here we need to work with width, not length. And why width, not length? Because it is the only parameter that determines the characteristic impedance. If the width is too narrow, the impedance is too high. If the width is too wide, the impedance is too low. Length has almost zero effect on the characteristic impedance, no matter how long you make it. Now that our line calculation is complete, we need to create a layout. Go to Window option. You can see the layout option. I will keep it as Cell 1. When you reach the technology settings, select the millimeter with 0.001 resolution. To keep our measurement precise, you can select other resolution if you want. With our width calculated, we have to draw a rectangle. You can see in the toolbar, or you can find it in the insert option. Now we need to change the width to the exact value we just synthesized. To do that, click on the rectangle. You can see the properties of this rectangle. Now copy the width and paste it here. As we said before, we don't need to worry about length. Here the length is 42 point something. We can set the length to 40. Now click on this icon. For better view, we can rotate the rectangle. To do that, we need to click on the rectangular, then press Ctrl plus R. Now you can see that the value has swapped. It doesn't matter because now this is our length and this is our width. You just have to keep in mind that where I am placing the pin, I will put some pin in the edge of the length. In the line calc, you can see there are 1 and 2 at the edge of the length. So we will put the pin here at the edge of the length. If we didn't rotate, then we have to put the pin here and there, basically at the edge of the length. Here what really matters is where you are inserting the pin. And why is that? Because by inserting two pins at the center of the edges, the simulator will know where the signal enters and exits, because we know signal will flow either from 1 to 2 or 2 to 1. That's why we will inserting pin here at the edge of the length. So to do that, here you can see in the toolbar pin icon, or you can find it in the insert option. Now you can see that I can't put the pin at the center of the edges. So to do that, to solve the problem, we have to put the rectangular at the center of the axis. To do that, just change the value here. At lower left x-axis, take half of the width, that means it will be 20, and so half of the 2.9396 will be 1.4698. Now you can see that the rectangular is placed on the center of the both axes. Now we can easily put the pin, insert the pin. See, put one here and another here. Next we have to set up the EM environment. To do that, go to EM option here, then go to substrate, create substrate. We need to change our substrate material. We will use FR4. To do that, go here, add from database. Here you can see FR4. OK, apply. I will set the thickness to 1.6 millimeter. That's it. Now again go to EM option. Here you can see the simulation settings. In this simulation setup, go to frequency plan. We will run an adaptive sweep from 2 GHz to 3 GHz and make sure to add a single point. Right at our design frequency of 2.4. Next go to option mesh. For better accuracy, I am setting the mesh to 80 cells per wavelength. Click on the edge mesh. Now go to output plane. Here select the save currents for all generated frequencies. Then run. Then click simulate. Once it's done, we can check our S parameters and Smith chart here to verify our 50 ohm match. Now my favorite part is the post processing. We can actually visualize the surface current distribution and animate it to see how the EM wave propagates along the line. To do that, go to EM option, first post processing, far field. Here you can see the 3D visualization. To see the animation, go to solution setup. Here select port 1, then 2.4. Go to plot properties. Then if you click animate, you can see the animation. And if you click port 2, it will just reverse. That means basically now the signal is going from port 2 to port 1, and when you click port 1 to 2, then it will come from port 1 to 2. If yours looks like this, then you have successfully designed a microstrip. If you found this tutorial helpful, please hit the like button and leave a comment below. If you have questions about the results, don't forget to subscribe for more engineering content. I will see you in the next video. Thanks for watching.